Alright, another draft physics video presentation. DraftScience here on YouTube. Yeah. DraftPhysics.com. Anyway, Franklin Hu has made another video exploring the theory of the transmission of EMF, electromagnetic, stuff. And so we have a sort of a debate about whether we can get to the core of whether there is or is not any need for an ether by getting into this subject of the nature of radio transmission, and who knows. So he's done a demonstration of the amplitude modulation, which is basically you take a carrier frequency that's kind of fast and you make it less of it or more of it, and you're sending a signal by doing less of it and more of it. And I would argue that you can just convert all of this into just a digital signal. Like the carrier is a digital signal of just a frequency, and then all you're doing is turning the carrier on and off, and that's all you really need to do to create a message. This becomes a bit, and this becomes a bit, and the stuff where there is nothing, that becomes a boop, and that's your dots and your dashes are really just something or nothing or something or nothing. So you can do an amp. You could have a 1 kilohertz signal here, a sound signal that's just really basically just turning this signal on and off. So this wouldn't be any signal here. So what it's really saying is you turn the carrier frequency on, you turn the carrier frequency off, you carry it on, you turn it off. So when they do the radar experiment, this is essentially what they're doing. They have the radar of 10 gigahertz here, and when they want to put an audio tone on it, they just turn it on and off, okay? And there's no real wave function to it, no real wave shape. It's just turning it on, turning it off, turning it on, turning it off. Obviously there's noise when you're doing that. Turning it on and turning it off becomes noise. But whatever, it's not really important to the fact that this is what you're hearing, is the digital on and off as a tone, as if it was a sine wave, but it's not a sine wave. It's just ons and offs and ons and offs, and it sounds like, well, you can't see that. It sounds like, okay, it's a wave, but it's not. So he sort of says in his comment that there's no analogs for digital, and I'd say the analogs are always kind of, yes, they're visual. I mean, a lot of equalizers will show you as little bars, of how strong the signal is, and it's in little bars. So it's clearly a digital representation of a curved line. So there are analogs, and I could argue that like submarines might have communicated with each other now and then by just pinging each other. They would send a little bit of a Morse code by just saying ping. They'd send, the ping goes pretty far, their sonar, so they could just send a signal to each other by just sending pings, ping, 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 and send messages. So I mean, it's not like you can't have a digital signal, a way of communicating from between one thing and another at a frequency. So that's all the whole real argument is about, is communicating the information, and whether or not there's any requirement that it be in any sinusoidal function, or there's any proof that when the actual information, whether it's photons or radio waves, right, it's all the same stuff, whether the photons have to be waving, that is getting stronger and getting weaker, or getting, going positive, going negative, going positive, going negative in some sort of gradual way, or whether it's perfectly duplicatable as just frequency, just bits that are a bit, no bit, a bit, no bit, no bit. And so I guess what I'm saying is, so far it's unconclusive. We haven't found the experiment that proves light is waving, okay, that's the nature of the frequency, or that a radio wave is actually waving, and it's not really just strength of how many photons you're sending is really the amplitude. The amplitude is just how many. That's all. How many bullets. So if you have a gun that can shoot a numerous, like I can shoot 100 bullets from the gun or just one bullet. And that's all you're really doing, is you're just saying, when I'm modulating the signal, I'm saying I'm going to press the trigger once a second, but I can press all the triggers or I can press just one trigger. So I can create a signal that looks like it's analog when it's clearly made out of digital bullets, a certain number of bullets. Alright, that's probably enough of a context. So the interesting part was, just a little bit of personal blah blah blah. He used this old, this used to be sold by Radio Shack, at least when I was a kid. And it's this 101 electronic project kit. And it's exactly the same kit I had when I was like 12, 13, something like that. I got it for my birthday. And it really, it really was the best present I ever got, And I burned up and blew up lots of stuff. And it was really interesting. The thing that really I obsessed about was the photocell. So there was a photoresistor. So as you change the exposure to the light, or a photodiode, well, this was really a photoresistor technically. Anyway, it would have more or less resistance. And that's the one that really fascinated me. Now the solar cell was really turned out to be important later in my life. Like when I was 17, I was working in a machine shop that it wasn't just a machine shop. It actually made industrial machines, but I was basically just doing circuit boards and machining panels for the controllers. So it was the controllers for machines. It was probably the better way to say that. That's mostly what it was making. Okay, but it did take the contract for whole machines, like they would say. So it was all really about alignment. So it was like 3 color printing. You have to print right on. You have to print with 3 different colors on the same surface. So you have to run the stuff through the machine 3 times. And the idea is it has to be really precise. Everything has to line up, or the colors aren't in the right places, and it looks shitty. So we made the controllers, little edge guides that would control exactly where the material was to make sure each time it went through, it was going through exactly the same. So there were, back then, the high tech was, red LEDs, and so it was photocells, which was really photoresistors essentially. So I was using the same technology that I'd learned in this little kit. And so that was kind of neat. But anyway, the solar cell came up because for this new other device, we had to see holes in clear plastic film. So it would come out of the machine, and it had to cut out parts that might have a defect. So you need a machine that could detect defects in the plastic without a person having to look at it constantly, coming through and fix it. So and the problem was we're using a bunch of these light sensing diodes, and the problem is that you couldn't really get it consistent. You couldn't get them all to be seeing with the same brightness, and so you couldn't get like if there was a hole over here, it was too sensitive at one side and was too insensitive at the other side. It was too much inconsistency. So even though they could react quickly, that is, they could see a small hole, you could never tune it to see the small hole, because it would be seeing too many holes in the other place. Well, anyway, and so I had thought about my kit, and I suggested, well, what about solar panels? So I cut the little solar panel out of the kit, brought it in, and we tested it, and it was quick enough, and it was really consistent. So you could put a bunch of solar panels next to each other, and you got the same amount of data, because it was actually generating the electricity. It wasn't opening and closing a valve and letting electricity through like a transistor. It was actually generating the electricity, so you could be really sure how much energy was getting to each panel, and it was really consistent, and it worked. And so it was like a $15,000 machine contract was based on this kit. And it was it was like the first time in my life that something, some silly little stupid thing I saw turned into something bigger, out of almost nothing. Now, I didn't design it, I didn't do this, and this, I just did what about, that was my contribution. But it, like I said, at the time, it felt kind of you know, significant. Like, wow, you know, out of this stupid kit came this, you know. So it's just this whole idea of what it does to you and does to your capacity to make a good suggestion. Like somehow your capacity to contribute is enhanced by the fact that you do have knowledge of these things. It gave me some kind of appreciation for the fact that I may have wasted an awful lot of my childhood, you know, not gaining knowledge of this stuff, and therefore not being able to make much of a contribution because I hadn't done as much work as I should have. So anyway, it's part of the becoming interested and obsessed, you know, and how this little toy really did play a big role in who I became. And just a fact. Just interesting that this is, you know, this piece of robotic instrumentation, you know, fed the ultimate conclusion that we're all robots, and this, you know, a lot of other thought was the implication of this. Now, I'm not too sure. My kit didn't have the integrated circuit in the middle, because I had to buy a new kit that had that in it. So the original one, I don't know what it had here in this. Everything else looks so familiar, but that's not familiar. Something else was here in the middle. Might have just been a logo, but I'm just saying there was something else in that middle. The transistors were over here. The coil was on the other side, actually. It was over here. So maybe that coil was over here, and they just filled in this space with the other stuff. So probably something difference like that. Yeah, that's probably just that's the only difference. Coil was over here, the knobs were here, that filled up this space, then the transistors, and then this stuff didn't have anything above it, the earphone and speaker jack and key jack or whatever. So that's probably the difference. Well, anyway, not a big deal, but it is a interesting bit of nostalgia. So I will read Franklin's comment to me. Alright, I guess I should read mine to him. 47 years ago, I got exactly the same kit as a birthday present. A couple of years later, I got the kit with some integrated circuits. Amplitude modulation can be easily modeled in particles. You just send more or less volume of particles at the same carrier frequency. So, say you were shooting a gun once every second, you just modulate by sometimes shooting 2 bullets at the same time or 3. The frequency is the same, but the volume of bullets is different. Obviously, the carrier frequency is much higher than the modulating frequency, so you have all kinds of freedom in terms of creating a digital shape. That is, the shape is going to be decided by the high frequency, and so you're not going to see it when it's digital. It's going to look like it's not, because there's so many little bits to the digit. He says, I did say that. Well, I wasn't really trying to repeat what you said. I just was trying to put it in more clear language so we both agree on why this doesn't prove anything. And I just want to make that kind of clear, because you do sort of imply that it might be proving something, and it's really not proving anything. Okay, anyway. That is what you would say, and you could change the volume of bullets. So, no, this isn't going to settle the question, but I think it is a victory. See, that's where I don't know how, if it doesn't settle it, it's not really a victory yet. That you agree that amplitude can be variable. Well, why would I disagree? In a radio wave, and it isn't like rocks hitting a wall. Well, it really is in some ways like rocks hitting a wall. It's just that you understand that you're just changing how you throw the rocks. But I still think it is far more plausible that it is just like a sound wave. Well, I think just like a sound wave, you're almost giving it away to me. You're almost conceding the argument to me, because just like a sound wave means it's pretty digital. Because a sound wave is moving through the atmosphere based on banging particles into particles into particles into particles. So it's still particles. Anyway. After all, that is what the sound waves do. I'm not sure whatever that means they do. But anyway, what they do is they're just particles. A bunch of them. You push something into a bunch of particles, and a bunch of the particles move. So it's still bowling pins, so to speak. We don't have any real world analogies or signals like that being transmitted by particles? Well, just because we don't transmit using big things, so obviously it's just an argument about what the little things are. And again, you're saying the little things aren't particles, and I'm saying clearly water and sound is particles. You can follow the banging particles, the atoms. The atoms are bumping into each other. That's how it's transmitted, so it's still particles. It's just that you didn't send particles. You're just having particles bang into each other. All right. And I'm just saying that you don't need particles to bang into each other for things like light and sound, that all you're really doing is just sending the particles. You're just throwing the dominoes. You don't bother having dominoes knock each other down. Alright, but it is just cool seeing the vintage kit and building the radio and hearing it receive a tone coming from my tone generator, which looks nothing like a radio transmitter. It's great that you have got the same thing. Yes, I don't know what happened to my original kit. Well, I certainly know what happened to mine. Yeah, I tore it to pieces because I'd find a use for the pieces, and so I'd build separate things with the pieces. So I know I did kind of I did tear it to pieces eventually. As I actually got a couple of the transducers for ultrasound. And that was really interesting. So I used the kit pieces to make the receiver and the transmitter for the ultrasound. Anyway, I had to buy mine from eBay. Yeah, I was thinking I guess I ought to look and see. I mean, they're probably very expensive, I would imagine. Anyway, it's a blast from the past, and I totally credit my advanced knowledge in electronics engineering, computer science, and my entrance into MIT to this kit. Yeah, I didn't know you went to MIT. I applied. I got a conditional response. If I would jump through hoop XYZ, they would accept me. But the bill was insane, so I said, I'm not going, it's too expensive. I mean, it really was 3 times as much as LSU, where I didn't go there either, but I did get accepted there. But it was funny that MIT was really expensive. It has made me the man I am today. The funny story is that when we first got it, I was just upset that we had spent so much of our Christmas present budget on this one thing, but it was one of the most important gifts I've ever gotten. Yeah, that's the tricky part too. See, it's kind of my father was a chemical engineer, and he didn't really invest in me in terms of talking science with me much. And we spent a good deal of time together. We went fishing every weekend, did certain things, and he just didn't invest anything. I guess he just thought I was a clunker. And it was my mother who saw that I broke everything and took everything apart and always wanted to know how everything worked. And so it was my mother who actually bought the present. And my father didn't even have anything to do with it or know anything about it. And so I really have to credit my mother for appreciating that I wasn't just a retarded kid who broke things. That there could have been something useful in the nature of me wanting to know how things worked. That it wasn't completely a destructive, or it could be motivated to become less destructive. But that was the dangerous thing, because once I got the kit, then I started doing all kinds of other shit and plugging crap into the wall and doing all kinds of things that were more likely to start fires and blow shit up. So it works both ways. It made me more capable of destroying more things, but also if it wasn't for that, I used to fix our TV. I used to do lots of stuff. So it all led to fixing cars and doing all kinds of other things. So huge. Kind of if you would say there was something that played a large role in who I became, it's got to be this stupid kit, this stupid balsa wood frame it was in. It's not really much to it. It's just the components on a piece of cardboard, but lots of little stupid pieces of wire, So even at first, you don't even figure out, oh, it doesn't matter. I don't have to use a red wire. I can use, because they're just lengths of wire. Like the black wires are long and the red wires are this, the green wires are short. And you figure out, oh, I don't have to obey these stupid color codes. Just little things like that as a kid. You don't realize at first you're trying to, obey the rules. And, and you figure out the rules are just stupid. I mean, they don't mean anything. But anyway. So anyway, just a little free personal story thing. And now I'll get to some kinetic energy stuff. So we'll pause and I shall be back. Alright, should be back. Alright, so thoughts on the nature of energy, kinetic, momentum, whatever. So just another reason to understand that it's just momentum. Energy doesn't need to be any more complicated than that. So you just have something, and you're saying it's moving in 3 dimensions of space. It's moving, and there's something else moving in some other way, and we're going to call that energy. And we're going to know that the argument can be made that we don't know by looking whether we're moving with this object or moving with this object, and how long these lines are. Which one is the accurate representation. This one's moving a little bit, this one's moving a lot, or whatever. It just doesn't really make any difference. That what we're going to call energy is the difference between those motions. And that's all there really is to the conversation. So that's the relativistic part. That just doesn't really matter. We just know that it is real motion in a direction. And the objects can have that motion. So then I can set up a circumstance where you have something like a bowling ball heading for some pins. Okay, and what is it going to do when it hits the pins? Is it's going to transfer its energy to some extent. Now as it's rolling, it's losing some of its energy to the floor. Okay, so the rolling is, bouncing on the floor and making some sounds and doing some stuff, and that's a little bit of friction. And we know that any friction slows this thing down. So we know that that's the energy for the friction comes from the object. So you have to move the energy from the object into some other thing moving. So that's energy lost to the object. The object has to lose energy to do any of that stuff. All of that stuff happens because this object loses energy. And the same thing is going to happen when it meets the pin. So if this thing's, say if this thing was going 16 miles an hour and it weighed 8 pounds, that 16 miles an hour is sort of the maximum amount of velocity it can give a pin. You can't give it more than 16 because it's going to hit it, and there's going to be a transfer, and as it's transferring, you could say it goes 1 mile an hour, then it goes 2 miles an hour, and then it goes 3. That in a way it's adding up the amount of speed it's getting. And the fact is, as soon as it's going fast enough, where this thing's going 16, and the thing you're hitting is now going 16, you can sort of understand that now it's 16.1, it's leaving. Okay, it can't keep giving it more energy because it actually isn't in contact anymore. It left. It's going faster than this thing. Its vector is faster, so obviously it can't give it more energy. So the maximum amount of energy the 2 pound, let's say, pin can get is 2 pounds times 16. That's the maximum amount of energy the pin can have from hitting the bowling ball. There's no other. It doesn't matter whether the bowling ball weighs 1,000,000 pounds, right? It could actually weigh 1,000,000 pounds. It just doesn't matter. If it's going 16 miles an hour when it hits the pin can only take 32 joules of energy. But it's going to take them. That means the energy is going to go 32 joules are going to leave the bowling ball, and they're going to go into the pin, and the pin's going to hit something. Now, what's it going to do? It's going to hit a wall. It's going to bounce off the floor. And so slowly but surely, the pin's going to ricochet around, and it's going to lose all its energy. And it's going to lose it to friction and denting things and moving things. Like they have a heavy tarp down, and the pin can hit the tarp, and the tarp will bend and move, and that movement will all be absorption of the energy. And now the energy's in the movement of the tarp, and blah, blah, blah. And so the energy's always going to end up going out eventually kind of as just heat. So it doesn't die, the energy. It just it goes into a form that we can't follow anymore. It gets so broken into little pieces and is inside of all kinds of things. It's just warm and this and that, and so it's going to just get converted. So I thought that was an important thing to just explain, why the maximum speed of the bowling ball will decide what the maximum speed of the pin is, what's the maximum amount of energy I can give to a single object. But obviously the weight will have a lot to do with what's my total amount of joules that I can give to numerous pins. So if I weigh more, then I can hit lots of pins and give away lots of my energy. And then the pins will give away the energy to the environment. That's basically how it works. So in theory, when you have this contest of what works better, the 8-pound ball or the 16-pound ball, clearly the argument is neither works better intrinsically, and that you could argue that there might be some advantages or disadvantages in the difference in the speed. So if you're going from a speed of 14 miles an hour to 16 miles an hour with a lighter ball, like if I split it, if I make it half the weight, 8-pound versus 16-pound, so we do 8-pound versus 16-pound, then we have to invert the miles per hour. Okay, so so clearly the 8-pound ball has a huge mile per hour advantage, right? Well, you can barely see that, but that's okay. So when it hits a pin, it can give it 16 miles an hour, where the heavy ball can only give it 8. But as I pointed out in a previous video, the heavy ball gives 8 and 8 and 8 and 8, where the lighter ball gives 16. Then the next time it hits a pin, it's only going to be, say, 14, and then 10, and then 8. So it will lose its store of energy much more quickly. So by the time it hits the 5th pin, it's only got, like 3 joules of energy left to give. It doesn't have the joules to now give the maximum velocity, where the heavier ball does. But anyway, the point would be is they're both basically equal, in the sense that the total amount of pin movement is going to be the same. You can't change how much movement you're going to get. You're just going to change how quickly the transfers are made, and whether the transfers, or how quickly the transfers are to the environment. So in some sense, you could argue the heavier ball has an advantage in the sense that you don't want the pin, like say if you were to hit this pin and move it this way, you wouldn't want to hit it with a whole bunch of your energy if the pin's not going to bang back into more pins. If all it's going to do is hit the wall and bounce into the gutter, then you've lost that whole piece of energy. You've lost the 32 joules, where if you hit it with only 8, then you'd only lost 24 joules. So you'd still have lots more energy to hit other pins with the ball, rather than hitting other pins with the pins. So it really depends on what you think the pins are going to do. Alright, but the thought I had that I didn't think about it previously, so I'm just going to point out something that hadn't occurred to me, is that if I did set up 100 pins, okay, inside a chamber, let's say that was made out of rubber, that's so all the energy stays. If a pin hits the side, it bounces back into pins. The idea would be is that it would be continuous, right? If I threw a bowling ball into here, it's almost like tipping a domino over. If I tip a domino over and it tips the next one over and it tips the next one over, it could go on forever, because the energy is not going to be used up by friction. So in this scenario, both balls knock down all the pins, and I could make it 1,000 pins, or I could make it 10,000 pins, or I could make it 1,000,000 pins, and theoretically both balls can knock down all the pins if I stop the pins from giving away their energy to the surface. So if I made the the sides out of rubber, so the pins all the energy would bounce back into the arena, you could theoretically say that the energy would just keep going right through all the pins forever. I mean, they'd all be hit in this direction. None of them would go backwards. So they'd all be going in this direction, and they'd just keep doing that. They'd just keep knocking each other over with the initial energy you put in with the ball. So the ball would lose all of its energy, give it to the pins, and the pins would just keep knocking pins down for what could be a very long time if I can get rid of friction. So if I can get rid of all the friction, it would just keep knocking pins forever, because the energy is forever. And when it goes into being friction, it's still forever, because it's created something that's hot. And that heat will be dissipated. And then something else will get hot because of that heat. And then something else will get hot because of that heat. And essentially the heat goes back into us, and then we use our heat to throw the ball and start it all over again. And so that's the cycle. So everything ends up as heat. And that was the thing around the 1800s that they sort of realized, is that there's a key connection between heat and energy. But what they didn't realize is there's a difference between the ball losing directly to friction, that is a direct conversion into heat, that is the rolling on the floor and heating the floor. That's directly transferring the heat into friction, and the indirect transfer of hitting the pin and then having the pin hit the floor and heat the floor and then heat the walls and heat the other things. So it's just a difference in when the heat gets, when you convert the energy into heat. And first you can just transition the energy in that you can hand it off to domino after domino after domino, and keep the same energy moving through the system. Now the dominoes are cheating because they're using gravity, so they're restorative. They get 100% of the heat back because they fall because of gravity. So the impulse doesn't have to be doesn't have to provide all of the knocking force. Gravity's doing it because we set them up. So we made the dominoes in some ways are a battery. They have their own energy, and we're just firing the energy of the domino. And so that's what makes it more perpetual. But anyway. But yeah, it all leaks. You're just talking about leaking. You're talking like it's you're transferring energy between buckets, and you have to recognize that some buckets have lots of holes in it. You've got the energy in your bucket, but your bucket has only 2 little holes in it, so you're not losing much, the bowling ball. And then you transfer some of it into the pin, and the pin is really leaky. Okay, it's going to hit lots of things. It's going to lose lots of its energy quickly. So it's all going to spill out, when you go put it into the pin. But then the one pin can possibly, before it all leaks out, one pin can hit another pin, so you can still get some more, transferred by pins, but it's all going to leak out eventually. And the key to using energy is to try to prevent it from leaking. Try to make all the buckets it's transferring to non-leaky, and then you can really get energy to go a long way. You can get it to do more than one thing if you can prevent it from escaping. You can get it to knock down lots of pins if you can stop it from leaking out of the system. Yeah, I think that's probably enough of a statement. Don't think there really hasn't been any comments of any use at all. No counter argument from Puro explaining why springs produce different amounts of energy. So he won't be able to defend that, and he probably won't apologize for it and won't concede he was wrong. So there probably won't be any further Puro comments for like 6 months. We'll have pretend this conversation was forgotten, and then you can start some new one. But it would appear that we're clearly at a point where there's no now it's really intractable. So until he advances the conversation with something more reasonable, there's nowhere for the conversation to go, because he has certainly no evidence that springs produce variable amounts of force. The same compression of a spring isn't producing the same force. Of course it is. So anyway, so that's enough of a video. Enough for now, anyway, this moment. We could check the comments, I suppose, and see if there's anything brilliant, but there probably isn't. And such. No. Same little trite blah, 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 blah. I mean, some guy keeps wanting to re-paraphrase what I believe or what I say, and so he did it again here. Is it fair to say you want explanation of physics that must be drawable as a picture? No, it doesn't must be. It must, again, this isn't that complicated. All of this is a trial. And you're saying, what kind of trial do you want? Do you want lawyers that tell the truth? Well, yeah, I guess I do. Do you want them to actually present evidence? Well, yeah, that'd be really great. Evidence is really great in a trial. So, yeah, let's have lots of evidence and then have the lawyers talk about the evidence. That's what I want. That's what I think science should be. Is rational explanations based on evidence. If you have a theory that that guy did something, energy does something, then show me the evidence. If you have a videotape and you can draw it, great. That's really good evidence. But you don't have to have that. You can have other evidence, like you found a footprint or a fingerprint or some DNA. There's lots of other kinds of evidence you can have, but it's got to be pretty good, right? It's got to have... It can't be like, oh, well, we left the DNA out for 6 days, in the sun. It's got to have integrity as evidence. We didn't do a 1 in a million thing or a 1 in a billion DNA code. No, it's really 1 in 10. It has the same code as 1 in 10 people. Yeah, that's not going to be good enough to convict them. I'm sorry. You need more evidence than that. That's what I'm saying, shithead. And is it fair to say some mathematical formulas don't easily translate into pictures? Well, they all should. That's the whole... Even Pirro sort of concedes that. That's the whole point of math, is to reduce all of the complex drawings into something much easier to manipulate. But they all should be drawable. You should be able to draw these proportions. When x is proportional to y or whatever, you should be able to draw it. So anyway, so I really don't need to keep being re-paraphrased by you. I think I've been fairly articulate in stating what I like. I like evidence, and I like good arguments. That's what I like. That's what I think science should contain. Shit. Alright. So anyway, enough of a video. So, until the next time and such, and so forth and whatnot. This has been a DraftScience video presentation. Thank you for your attention. Such.